All right, thank you very much for not talking any further. So today we are very fortunate to welcome Professor Alyson Brooks, who is visiting us from the University of Rutgers University. Rutgers, sorry. I'm foreign, I'm sorry. So Alyson obtained her PhD from the University of Washington working with Fabio Governatto, following which she had postdoctoral stints at Caltech and University of Wisconsin-Madison. And then she moved on to Rutgers, where she has been a professor for the past 6 years. And she very recently won the Maria Geppert-Meyer Award from the APS for the pioneering work that she has done and the rest of the group has done on improving our understanding of dwarf galaxies, how they form, and what they look like, essentially, through cosmological simulations, which is what the focus of our talk today will be, and I will leave it up to you.
Thank you very much. Yeah, so I basically thought I would give you guys an update on the status of dwarf galaxies and cosmological simulations. That's what you're seeing here. This is one of my simulations. The green is all dark matter. Andrew Ponson really likes dark matter, or green, so he always makes the dark matter green. But these are all dwarf galaxies sitting in these cosmic filaments. And what you're seeing here, the rest of it is just a temperature map of gas. Right, so this is hot gas that is being heated up by supernova feedback in these galaxies. And so the really hot stuff is white, and then you can see it's expanding out of these galaxies, and it turns yellow and red as it cools. But it's really filling the space in between these galaxies as well, into the IGM. So I figured I'd give you a brief history. Right? There's been a lot of progress in the last 5 to 10 years, really, on successfully modeling dwarf galaxies in cosmological simulations, both in terms of actually making things that look realistic, their structure, and figuring out, can we get the abundances right? So I'll talk about that. And despite the fact that a lot of simulators use different star formation feedback mechanisms, we do generally tend to agree that we make realistic galaxies. And so I'll talk about why that is, but really it comes down to the fact that galaxies self-regulate. However, that's going to be a problem in the future. We are now starting to push into a regime where we're getting higher and higher resolution. We're starting to resolve things that look like ultra-faint dwarf galaxies, and these are going to be galaxies that can no longer self-regulate. So we're finding that some of the modeling that we've been taking for granted is actually going to be a big concern in the future. And so I'm going to highlight a couple of the key things we've been working on there. So let me start with some of the successes. And I always like to start with this fact, right? The fact that we can now make bulgeless dwarf disk galaxies. So what do I mean by bulgeless dwarf disk? Well, here's a nice picture of the Whirlpool galaxy. People are used to seeing this big stellar bulge sitting at the center of this galaxy. But it turns out most dwarf galaxies look more like this, right? Where they can be described as an exponential disk all the way to the center. There is no stellar bulge in that galaxy. And if you want to look at it a little more quantitatively, here is some data from Van den Bosch et al. 17 years ago now. But what you're seeing in these gray hashed regions, this is a different dwarf galaxy in each one of these panels, and you're looking at the angular momentum distribution of the gas, cold gas and stars of these galaxies. The black line is the same in every panel, and it's the angular momentum distribution that you expect for a typical cold dark matter halo. So in cold dark matter galaxy formation theory, we think that galaxies get their angular momentum through the tidal torques from large-scale structure. And since gas and dark matter are initially well mixed at early times, the gas and the dark matter should start off with the same angular momentum distribution. So what you can see in every panel here, however, is that they do not have the same angular momentum distribution. And in fact, there's always this tail of low angular momentum material that's missing in the dwarf galaxies. Okay. And that's partly because they're bulgeless. So I'm just going to jump to what I think the solution is. Right? It's the same thing that was in the intro slide. It's these outflows. Okay? So we started being able to simulate realistic bulgeless galaxies when we started being able to simulate outflows. Okay, so this is a dwarf galaxy. It's about 10 to the 10 in halo mass, 10 to the 8 in stellar mass, and it's sitting in here right at the center. It's actually edge on. However, it's a dwarf disk, right? So it's like a kiloparsec across, so it's really down there sitting at the center. And this movie is made at a time when there's been a burst of star formation. There's been subsequent feedback from that burst of star formation that's heating up the gas, and the gas then expands and it's leaving the disk. And you can see it preferentially tends to come out perpendicular to the disk because it's just following the path of least resistance. The black line is roughly the virial radius of this galaxy at this time step. So some of this really is just leaving and never coming back, right? There is a galactic fountain effect going on here too, but it's really hard to tell in this movie.
Question.
Mm-hmm.
So the stars are subdominant in terms of the mass of these dwarfs, right?
Mm-hmm.
It's a dark matter. So are you
Absolutely,
saying
it's dark matter
the angular
dominating.
momentum distribution, you describe that it's actually the mass distribution of the dark matter?
That's right. Yeah.
So you're saying the dark matter is pushed out by the outflows of the gas?
Yeah. So I haven't gotten to that part yet, even, right?
But that's what you're
that's part of it. But really, here I'm just focusing on the gas, right? So most of the star formation, because we are talking about these dwarf galaxies, most of the star formation is really occurring at the center of this galaxy, and it is then causing a lot of the gas to leave, right? So it's the gas. If the gas starts off with the same angular momentum distribution as the dark matter, then there should be this lowering momentum tail that settles to the center of the galaxy and goes on to form a stellar bulge, right? And now you're removing essentially that material in order to go on and form a stellar bulge. And so if I take this simulated dwarf and I make the same type of plot at redshift 0, this is the angular momentum distribution of the cold gas and the stars of this galaxy, and you can see it now looks much like we see in real dwarf galaxies. The purple dashed line is the angular momentum distribution of the dark matter halo, so it looks like what you would expect, again, for a typical cold dark matter halo. And the nice thing about particle simulations is I can go back and I can find all of the particles that ever belonged to the galaxy, and I can ask what was their angular momentum before it got kicked out. And so if I do that, you get this red line. Right? So it is that the gas and dark matter initially does start with the same angular momentum distribution, but then you modify it through these processes. And so yes, as you just mentioned, right, that also affects the dark matter. So here is the dark matter density profile of that same dwarf galaxy as a function of redshift. And so as it comes back around to high redshift, right, you can see it starts off initially very steep, very cuspy, very much like your typical NFW cold dark matter halo. And then with time, it actually starts to flatten. And at redshift 0, it's got a nice core density profile. Okay, so what is, as was mentioned already, what's happening here is that despite the fact that these things are dark matter dominated, the gas can cool to the center of the dwarf galaxy. So the gas and dark matter densities are actually comparable, very at the center. So when you then take that gas and you get rid of it through these outflows, you alter the gravitational potential. And so you end up in a galaxy like this. It has a very bursty star formation history. So you end up fluctuating the gravitational potential over and over again. And so you end up pushing dark matter out of the center of this galaxy and transforming what is initially a steep density profile into a chord profile. And so this is just a comparison on this side of two simulated galaxies right here in the yellow and green, compared to data from the THINGS survey, the H1 Nearby Galaxies survey. And in those dwarf galaxies, you can see that all of them tend to be chord. The gray lines are what you would expect for an NFW profile. And so all of them tend to be pretty much chord, and the simulated dwarf galaxies were actually done, we made mock observations of these dwarfs so that we interpreted the cores in exactly the same way as the real galaxies, and they end up looking very much like the observational data.
So I see that the core shift develops very late. So for ultra faint, since they're dead since H11, you expect all of them to be
We do not expect this to happen, right, in ultra faints. Okay, so this gravitational potential well fluctuation is particularly effective right, it depends who you talk to, but somewhere around here probably, about 10 to the 8 in stellar mass. That's sort of the sweet spot where the gravitational well is shallow, but also deep enough where you can get this repeated cooling of the gas and keep having this bursty star formation history. As you go to lower stellar masses, you don't seem to have these repeated bursts, right? Either you basically don't form enough stars to have enough energy injection, or maybe you only undergo a burst and then you get rid of all your gas and you're done. So we don't actually think that ultrafaints should have core galaxies.
So what do observations tell us?
Right. Well, who knows? Right.
Whether it's a blue or
Okay. Yeah, I don't know which one that actually is. I don't, but this is not an ultrafaint galaxy, right? This is a classical galaxy right here. So just to be fair, right, this is the slope of the dark matter density profile measured at 500 parsecs, actually between 3 and 700, as a function of stellar mass, since I didn't actually explain that.
How sensitive is this conclusion to the exact description of star formation?
It seems to be, well, okay. So it seems to be if you have high enough resolution, basically if you can resolve high density peaks in your gas, that this comes out of the simulations. But if you don't have high enough resolution, if you have low densities, then essentially when you have the star formation and the feedback goes off, it's going back into low density gas that is actually very good at getting rid of that energy. And so you don't have this same effect where you're dumping energy into these high density peaks and it becomes this very efficient outflow. So it's resolution dependent.
This is all star formation feedback. What about black hole?
No, yeah, nobody's done that yet, actually. So let me first say, like, here are a bunch of observations, right, to answer your earlier question. Here are a bunch of observations in blue. These are all in the classical dwarf range. They do tend to look like they have cores. Okay, now to be fair, this is a hard problem. Something like Fornax at about 10 to the 7 in stellar mass, right? There's one data set out there pretty much. Matt Walker gathered, thousands of stars in Fornax. And people use that one data set and they come up with different answers for whether or not they think that Fornax should be, whether or not it has a cusp or a core. Okay, so people don't agree to begin with when you've got a lot of data. And if you want to test this down here in the ultrafaint range, right, now you're pushing towards smaller radii and a lot fewer stars. And so there's no consensus yet on what's going on down in the ultrafaint range. At higher masses, simulations tend to agree that as you head back towards Milky Way masses, things start looking cuspier again. Right? And that's just because the potential well in the Milky Way is so deep that you don't have the same effect, essentially. It can't overcome the deep potential well. Having said that, no simulator to date has run it yet with black holes and stellar feedback that can do this as well. Right? So if AGN feedback also have the same effect, where they can rapidly fluctuate the gravitational potential, then this answer may be wrong. Right? So I'm kind of agnostic about whether or not the Milky Way should be cusp or core. Any other questions?
So any dead system that's been dead for a long time is going to go back to a cusp, or and you make it a core?
Not necessarily. If it made a core initially, and then it stops forming stars or something, it could stay a core. But other people have shown that if a late merger comes in, that's exactly what's going on here. This galaxy is undergoing a merger at Redshift 0, and it's driving material back towards the center to make it cuspy again. And so mergers can reform a cusp.
But it also depends on the size of the core, right? Because there are some simulation that some people claim if you make a core but it's early enough, then it actually goes back to cusp. Right? I mean,
Just
you
through
make
accretion?
a very small core initially, but then take it so long, right?
Fair enough. Sure,
then,
just through extra accretion, I would assume in that case, in contraction. Okay, so let me actually turn to abundance. Okay, so what you're looking at actually on the right-hand side here is the too big to fail problem. So if you focus on the red, this is data from the Milky Way's dwarf spheroidal satellites. In blue is data from M31 satellites. And so plotted as their circular velocity as a function of luminosity. And I have run 2 Milky Way mass galaxies as dark matter only, and their satellite galaxies, the circular velocity versus an assigned luminosity, end up as these black circles. Right? And so you can see that if you run a dark matter only galaxy, the simulations tend to lie systematically to higher masses than the observed data. Right? And the reason that's the too big to fail problem is that somewhere around here, it's generally thought that galaxies above this mass should be able to hold onto their gas and go on and form stars. So they are too big to have failed to form stars. So the question is, where are they?
What does MV mean for a dark matter only?
Yeah, so you have to assign, right, a stellar mass and turn that into a luminosity. So these simulations are run actually with both dark matter only and then over here with baryons. So I could actually just take the luminosity from the baryonic run and assign it to the same halo in the dark matter only run. Right,
so they do form recognizably the same halos?
Yes, yeah. You
One
can
to
actually
one
track. You can actually track the dark matter particles
Okay.
between the simulations and find them in matching halos. Okay, so if I take these two simulations and I then just add baryons and rerun them, this is instead what I get for the dwarf toroidals, right? So the black points here are the things that end up being gas-free, so they are true dwarf toroidal analogs, and these empty circles here still have some gas in them. Okay? But for the dwarf toroidals, you can see that all of these things start off systematically too high in a dark matter only run, and then they end up matching the data when you add baryons. So what's going on? The first answer is over here, and when you add baryons, you also get a disk. Right? So in the case of a dark matter only run, you have no component that can cool to the center of the galaxy. But then when you add gas, you then have a component that can cool to the center of the halo and go on and form a galaxy sitting at the center of that halo. So that means that there's now extra mass at the center, there's a disk potential, and as satellites orbit around that disk, they feel stronger tides. And the tidal forces actually end up removing more mass from these satellites. And the closer your satellite comes to the disk, the more tides it's going to feel, or stronger tidal forces. And so the galaxies over here that lose more mass are the ones that actually come closer to the galaxy. They have a smaller perisphere. Okay. At this end, there's an extra effect going on, which is that these bright galaxies over here are also massive enough that they can go on and start forming a dark matter core before they infall onto the Milky Way. And so that means that they end up with a lower binding energy, and so it's easier to strip mass from them after they fall in. So these guys can start off with a higher mass and actually end up in the same range of velocities as the lower mass satellites, or lower luminosity satellites. And then there's another effect, right, when you add a disk, which is that some of these things will come close enough that they might even pass right through the disk and become completely destroyed. And so these, if you can see these things highlighted in red, these are satellites that survive and will survive indefinitely in a dark matter only run, but do not survive when you add baryons. So this first effect here is just to show you that you can actually bring the velocities in line with the observations. So that alleviates the too big to fail problem. And if you take the rest of all of these effects into account, you can basically reproduce the distribution of satellites that we see around something like the Milky Way or M31. So we showed this using Via Lactea. All right, so Via Lactea is a dark matter only run of a Milky Way mass galaxy. It has a publicly available catalog. You can go grab all the satellites in Via Lactea at redshift 0. And we looked at the circular velocity within 1 kiloparsec of all those satellites. And again, you have to assign a luminosity. So we did this based on the stellar mass to halo mass relationship in our simulations. And in Via Lactea at redshift 0, right about here is the luminosity of Draco. Right? So in the Milky Way, there are a dozen galaxies brighter than Draco. And in Via Lactea, there are more than 100. Okay, so that's the missing satellites problem right there. Okay, and most people think that if you just consider reionization, that you solve the missing satellites problem. And indeed, if I consider reionization, then all of these halos here that end up with empty circles are too small to have held on to their gas. They shouldn't have gone on and formed any stars, so they end up being dark at redshift 0. The problem is that actually leaves this entire population up here. Okay? So the Via Láctea would predict that there's something like a dozen or more fornaxes wandering around the Milky Way, and there's not. There's one, or two, depending on if you want to call it Sagittarius, maybe. But if you consider what a disk should do, right? There's no disk in Via Láctea because it's a dark matter only run. Then all of these things here that end up with a little cross in them come within 20 kiloparsecs of the center of the halo. And they should actually have interacted with the disk and been completely disrupted if there had been a disk there. So when you take that into account, you're left with this red distribution. That's it, right? So now you have the number and velocity distribution and luminosity distribution that ends up looking like something like the Milky Way or M31. Okay, so that's abundance of the satellites. Okay. You may have also heard that there is an abundance problem in the field. So this is the H1 velocity function of observed galaxies here. This is data, it's mostly taken from alfalfa, but it's a mix of local volume and H1 data. But the black line is what we actually predict in cold dark matter. Right? A steeply rising velocity function. There are more small galaxies than big galaxies. And if you look at the dwarf galaxy scales, down at about 20 kilometers per second, there's actually about an order of magnitude gap. So some people have interpreted this as a missing dwarf problem in the field. Of course, we're not actually comparing apples to apples when we make that comparison. Right? The theory version of it has a dark matter only simulation, and for every halo in the volume, they can make a resolved circular velocity function, and then they are assigning the maximum value of that rotation curve to be the velocity that they would expect to see for an observed galaxy. That would be nice if all the observers had this for every galaxy, but they don't. It's alfalfa. It's unresolved data. Right? What they actually have is the H1 profile of every galaxy. And so this is just in case you've not seen this type of classic double horn profile before. Right? If you've got a disk galaxy, the side that's rotating away from you is going to be redshifted, one side's going to be blue shifted, and so you end up with this classic double horn profile for the H1. And so what the observers are doing is they are taking the width of this profile at 50% of the peak height, and they call that W50, and they are assuming that that corresponds to the rotation of the galaxy. Right, so we're comparing two different things here. So we can just ask with simulated galaxies, do those two things match? Right, so here are three simulated galaxies, one at Milky Way mass, and you get this classic double horn profile. This one's about 100 times less massive, and this one's even more dwarfy. Right? And you can see as you go from Milky Way to these dwarf galaxies, you change from this classic double horn profile to something that looks much more like a Gaussian. Okay? And we see that in real galaxies, right? So that's sort of the observed trend that we see in mass, and that's going to be important again here in a minute. So I have mock H1 data, and I have resolved rotation curves for all of these galaxies, and I can just ask, do they match? And if they match, they should all sit here at 1. And the answer is no, they do not match, not even close. Right, so for things more massive than about 100 kilometers per second, you actually would get a higher velocity than you would expect from theory. And that's been known about for a while, right? That's just the fact that baryons can cool to the center, they can trap the halo, and you end up getting a higher rotation value. But the dwarfs, you can see, really, end up being at 50% of what you would expect, or more, even. Okay. I'll come back to why that is here in a second. The other thing that you have to consider is whether or not you can detect all of these galaxies in the observational data. The H1 velocity function that I showed you, they think they're complete down to about 1 million solar masses in stars. And so here is, for all my simulations, the fraction that have more than 1 billion solar masses as a function of Vmax. And you can see right below, right at about 35 kilometers per second or so, it starts to tank, right? You start to lose a whole bunch of dwarfs from your survey. So if you put those two things together, right, the fact that the velocities don't match and that you are not complete at dwarf scales, the dashed line is, again, the theoretical prediction you would expect. The black line is what you get if you just take into account detection, right? So you start to lose all these dwarf galaxies. And then if you take into account the velocity shift I showed, it essentially ends up pushing stuff from the theoretical line over this way. And now you end up with these predictions in blue, which pretty much match the data precisely. Okay, so in this case, we've just done an apples-to-apples comparison, and it accounts for the difference between observations and theory. And so if you're curious why that velocity shift happens, okay, this is maybe not surprising to most people. It is well known that in dwarf galaxies, when we measure the rotation curve, the outermost H1 data point is still on the rising part of the rotation curve. Right? So we tend not to measure Vmax in these dwarf galaxies. And that has been understood for a while. But it turns out that if you use W50, the H1 profile width, you don't even measure the outermost H1 rotation curve. Right? And if you use W20, with a 20% of the peak height, you do. Right? So that you can see that just because of this Gaussian shape. In dwarf galaxies, because they have this typical H1 profile, if you measure it at 50% of the peak height versus 20, you're going to get a very different answer in terms of velocity for the galaxy. The case is not the same in these more massive galaxies because this H1 profile drops off so steeply. Measuring at 50% versus 20% of the peak height barely gives you a difference. So basically just taking into account the observational biases. So when I talk to observers, they tell me that's a theoretical bias, right? But taking into account the biases between the theories and the observations can reproduce these discrepancies. So I don't think there actually is a missing dwarf problem in the field either. Questions, comments before I move on?
Are there other trace-offs that can be used observationally to get a better handle on the vision curves at larger radii?
Yeah, I don't know yet. That's a good question. So we still have to work on that. You can. Sorry, I'm going to do this thing I don't usually like to do, which is you might be able to take something like this, right, and sort of extrapolate. Well, if all of the data follows some sort of trend like this, then I should be able to sort of extrapolate what the dark matter only Vmax should be from that. But we haven't pushed it to that point yet. Yep.
So adding baryons in the way that you do, does that help in any way to reproduce Tully-Fisher relation?
Actually, let me show you we get it right. So this is the baryonic Tully-Fisher relationship for the same set of simulations. Does it help? That I don't know yet. Yeah.
Oh, but the simulation was, so before you showed V as a function of the magnitude, there it was more scattered. Is that because the sun has light radiation?
Satellite. That's because they're satellites versus field central galaxies. So most of the scatter in the satellites actually comes from the pericentric passage and how much tidal forces they felt. But for our field galaxies, which are not satellites, you actually end up with a pretty tight relationship.
Would you expect scatter because of the different star formation histories? There should be scatter.
Apparently not.
You have a tight, so what explains the tightness?
I don't know. This is baryonic Tully-Fisher relationship, particularly in dwarfs, is still something that I'm very interested in looking at and trying to explain. I don't have a good answer for that yet. Okay. So I wanted to point out, that a lot of these types of results, or particularly matching scaling relations, come out of a lot of different simulations, right? And so that's what this plot is showing you, is the fact that these simulations match a whole bunch of scaling relations. Here's the stellar mass to halo mass compared to inferred abundance matching, the size luminosity relationship, the baryonic Tully-Fisher relationship. They also match the mass metallicity relationship. And that same work on the H1 velocity function, we also looked at the gas fractions and the sizes of the disk as well. And we're not the only ones, right? So I like picking on this paper here from Almer et al., where they match everything in their abstract, right? So here's a set of Milky Ways. They match the stellar mass to halo mass relationship as a function of redshift. They have the star formation rate, sizes, gas fractions, and metallicities as a function of redshift compared to observations. And they have realistic morphology, surface density profiles, and rotation curves, right? So pretty much everybody is matching everything.
But the problem is that some observations might be wrong, so if the simulations match all of those.
Tell me about it. Yes, I'm going to agree with that statement. Yeah, okay. But, you know, we're all using different prescriptions, right? And so the question becomes, why is it that when you have a bunch of different star formation and feedback prescriptions, you can still end up matching all these different scaling relationships? And as I hinted at earlier, it's because these galaxies can self-regulate, right? So there have been a bunch of papers now that actually showed how galaxies do this. But this is one example from Benincasa et al., where they took an isolated disk galaxy and they just changed all of these different parameters. So here's what happens if you change the star formation density threshold, right? So going from 100 AMU per cc up to 1,000 for when your star formation is allowed to occur. And it essentially has zero impact on the pressure in the disk midplane, so you end up with the same star formation rate. You can change the star formation efficiency, that's what C star is, by, you know, basically a couple orders of magnitude, but you don't see a couple of orders of magnitude change in the star formation rate. And when you do change the star formation rate, the feedback then basically suppresses you from forming more stars, right? And if you form more stars, you get more feedback. That feedback then damps down more star formation. So these galaxies are really good, even when you change these parameters, at self-regulating so that you end up with similar galaxies. Okay. Here's another example of in a dwarf case. This is a galaxy at about 2 × 10⁷ in stellar mass. It's been run with 2 different star formation prescriptions. So in this case, we have a classic density temperature threshold. So when your gas gets cold enough and dense enough, there's some chance it can go on and form stars. And in this case, it's if you get below 10⁴ Kelvin and above 100 AMU per cc, then you can go on and form stars. And here's the resulting star formation history. This is the exact same galaxy, but now run with a prescription that tracks the formation of molecular hydrogen in the simulations. So the formation and destruction by Lyman-Werner radiation. And so in this case, you know, you actually get a star formation history that looks somewhat different. And notice that the y-axes are actually on different scales, but you end up with a galaxy with the same stellar mass at redshift 0. Here's another one. Here's a slightly more massive dwarf galaxy at about 10⁸. This has been run with 3 different star formation prescriptions. Basically the 2 I just described, and another one where there's no metal cooling, but is otherwise a density temperature threshold. And you end up with pretty much the exact same rotation curve. And if you track the outflows from the galaxy, they're all the same to within a factor of 2. So that, I think, is why we've been so successful in the last decade at making realistic dwarfs across all these different groups. The problem is going to come in the future, right? As we push down to smaller galaxies, because we're hitting higher resolutions, people are now starting to want to make predictions for ultrafaints, especially, right, we've got LSST coming online, and LSST is supposed to find us hundreds of dwarf, right, ultrafaint galaxies. This is a classic plot from Eric Tollard and collaborators showing us that we're biased. And so down here we've got the ultrafaint dwarfs. We can only find things that are nearby, right? But here's the prediction for single all-sky survey of LSST and the co-added LSST data at the end of the survey lifetime. Right, so at the end of LSST, we should have apparently found, you know, several hundreds of dwarf galaxies out to a megaparsec. So that's pretty exciting. And so to prepare for the future, right, like I said, people are now pushing to these higher resolutions. We've been doing that in my group partly through running what we're calling dwarf volumes. Right, so this is one dwarf volume. And this movie is it's just done at redshift 0. You're looking at the dark matter distribution and the gas distribution. You know, it's a dwarf galaxy, so it's like not that exciting, right? It doesn't have like grand spiral arms or anything. But when it comes back around here, we're zooming in on the most massive dwarf in this volume, which happens to be about SMC size. Right? As it comes back around here, you can see that what we've done essentially is your classic zoom-in simulation, but now rather than putting all of our resolution elements on one halo, we've actually done a cosmic sheet so that we get a whole bunch of dwarf galaxies out at the end, a collection. Okay. And so we've now done this 4 times. Right? So here are our 4 volumes. You just saw Captain Marvel. We've got Electro, Rogue, and Storm as well. They're all done. They've all been run to redshift 0. They have force resolutions of 60 parsecs. The SBH softening, or yeah, not softening, sorry. I'm missing a word here. The SBH resolution can go down a factor of 10 further to about 6 parsecs. They've all been run to redshift 0. They've all been run as dark matter only, and they've been run with that molecular hydrogen star formation prescription I just told you about, and a prescription for black holes. So we're also looking at the prevalence of black holes in dwarf galaxies and active black holes in their histories. And Captain Marvel, we've also run with this second star formation prescription, the temperature density threshold that I told you about earlier. Okay, so I'm going to come back to that in a bit and tell you about some results from that. So in addition to these, we wanted to do, these are volumes that are somewhat further away from Milky Way. So the dwarfs in these volumes range from about 4 to 10 megaparsecs away from Milky Way. So they're still local volume-like, but they are further away than the things that are right nearby. And so to get the full environment, we're also running a group of Milky Ways. And so since we named our dwarfs after the Marvel comic characters, we figured we would pay homage to the other famous comic book publisher and name our Milky Ways the DC Justice League. However, we liked having 4 women. So here's our DC Justice League. We've named them after the 4 women who have served on the Supreme Court. But they also reach basically comparable resolutions to these dwarf volumes. They've all been run at 170 parsec resolution all the way to redshift 0. These things are beasts, right? They're like 20 million hours a piece. So they're still going. I'm not actually sure we're going to get them all the way to redshift 0. But they offer, we're getting at least one down to redshift 0, and it's going to offer a nice comparison of the environments. By the way, these are comparable to, if anybody's familiar with triple latte from the fire group, they're on the same order. So the whole point is to get out a statistical sample of dwarfs. So here we are. We've got a couple hundred dwarf galaxies at redshift 0. This is their stellar mass to halo mass relationship. So one thing we're also working on is updating our predictions for the slope and the scatter of the stellar mass to halo mass relationship at the low mass end. But let me tell you about some issues we found in here, right? So here you can see we're actually now pushing down below into the ultra-faint dwarf range with these galaxies. And so we're starting to notice, right, that these are things that are no longer self-regulated. So one of the things you have to worry about when you run ultra-faint dwarfs is the IMF. And so my grad student, Elad Applebaum, had a paper out 2 weeks ago, I guess now, on implementing a new method to deal with a stochastically populated IMF. So in real dwarf galaxies, if you have stochastically populated star formation, then you do not converge to the full IMF, right? So we do not expect small galaxies to have necessarily the same number of massive stars as in a fully populated IMF. And the convergence is at about 10 to the 5, right? So if you get above about 10 to the 5 in stellar mass, then you start to look like a fully populated IMF. So what Elad has done is, there's a scheme out there where a lot of people are already trying to deal with this through quantized feedback, where basically what they do is they draw from a Poisson distribution to figure out if the supernova should go off or not for a star particle. But what Elad did is he actually decided to track every single massive star in a star particle. So here are 3 different star particles. They all end up with the same star particle mass, right? That's one of these constraints from cosmological simulations. We know how big our star particle should be once it forms, right? We want it to have a certain mass. So Elad's new prescription now stochastically populates the IMF across the full range of masses, and then when you get to that particle mass, he uses something called the stop nearest method, which basically just says, I draw something and it went over the mass of the particle. If I keep it, am I closer than with whether or not I get rid of that last draw, right? So that's how he does this. And then he reapproximates, he keeps all of those little individual high mass stars above 8 solar masses and reapproximates the low mass end as continuous again. And that way we don't have to keep tracking all those individual low mass stars, we're just worried about the high mass stars that are going to go supernova 2. Okay, so here are 3 different star particles, all with the same masses. This one ended up drawing something like 7 or 8 high mass stars. This one had 3, and this one had 2, because of the stochastic population. The star particles in here are, I think, 1,000 solar masses each. Okay. So down below here are the resulting supernovae that go off. So if you approximate as a continuous IMF, then you get this continuous injection of energy, whereas if you have these discrete stars going supernovae, you now have these discrete bursts of supernovae going off. And notice we assume that everything above 40 solar masses goes into a direct collapsed black hole, so these actually don't contribute any feedback, so that's why you only see 1 star particle down here. Okay. So that turns out to have an impact on the resulting stellar masses of the galaxy. So this is the same simulation run with this stochastically populated IMF versus continuous IMF. And down below about 10 to the 5 in stellar mass, it turns out that all of these stochastically populated IMF galaxies tend to have lower stellar masses. And this is the exact same thing, just the comparison of the 2 stellar masses as a function of their halo mass. Okay, so what is happening is that it's really these low mass galaxies, these things that can no longer self-regulate, right? We're blowing out a bunch of their gas through this discrete supernova burst now, and we're reducing their ability to form stars. And that's shown a little bit better here. This is the burstiness of the supernova feedback in the stochastic case versus continuous. So we get more bursty star formation, like I showed earlier, and that impacts the gas particle temperatures. So in the stochastic case, we heat up more of the gas and we have fewer cold gas particles available to go on and form stars, and so we end up with less star formation inside of these ultrafanes. Yeah?
So this is about the supernovas. Now what about the other side, about again, the prescription for the star formation? If now you change, for example, you have a different metallicity and you have different cooling and maybe a different threshold for the star formation, would that also have a strong effect on?
Yep. All right. So IMF is one thing you got to worry about. Oh, yeah, you have questions before everyone?
Yeah, sorry. In the previous slide, so what exactly is how exactly you quantify burstness?
It is a ratio of the mean over the standard deviation plus 1 over the mean over the standard deviation minus 1. It's just this classic formulation for Percy. Okay, so yes. Star formation prescription matters, it turns out. So here is the Captain Marvel volume of Dwarf Galaxies, where we ran it with the temperature density threshold. So we call that our metal cooling run. That's what MC stands for. So when gas in this gets below 10 to the 4 Kelvin and above 100 AMU per cc, there's some probability it will go on to form stars. Over here, we have the same prescription where we follow the formation and destruction of molecular gas, and then we say that you have to have molecular gas present in order for stars to form. And so at the higher masses, we have a 1-to-1 match, where there's a bunch of dwarf galaxies up here that show up in both runs. But you can see there's a big difference down here at the lower mass end, right? So it turns out this run makes a lot more dwarfs, ultra-faint dwarfs. And the stars, in fact, are satellites, right? These are satellite companions around these dwarf galaxies. So it makes more dwarfs, and it makes a lot more satellite dwarfs. And actually, it ends up making about 5 times more dwarf galaxies in this run than in this run. And so what's going on is, right, we're following the formation of H2. So these are really tiny halos at high redshift, basically no metallicity, right, or down around 10 to the minus 3 if they have any metallicity. And so the formation time for H2 is longer than the reionization epoch. It's several billions of years. And so that means we just don't form any molecular gas before reionization essentially removes all the gas from these halos and stops them from forming stars entirely. Right, so I don't know what the real world is doing. You know, I'm not saying one of these is right, but it matters. It definitely matters. So here's a couple of impacts that it has. This is the predicted stellar mass function that we would get from these 2 different runs. And the blue and the green are just if you take into account just the number difference between those two, the fact that one produces more dwarfs than the other. But the orange line takes into account the fact that if you look here, the H2 run also ends up with a steeper stellar mass to halo mass relationship. And so if you take into account the steeper stellar mass to halo mass relationship, you end up with this orange line. So the gray is the region where ultrafaints have been found by DES. Right, so this is, you can really see that it's going to make a big difference in this range, right? So our predictions for what LSST should find are going to vary dramatically based on what star formation prescription we use. And like I said, there are a lot more satellite ultrafaint dwarf companions in the MC run. And so here are our predictions for the fraction of isolated dwarfs that have 10 to the 10 in halo mass that should have ultrafaint satellite companions. This was done with FIRE. This is the results from Wheeler et al. And their prescription, that was FIRE 1, for those of you who are familiar with such things. But that was a little bit more similar to our MC run. Right? So those results are somewhat comparable. But then the H2 run really shuts down any ultrafaint dwarf formation in these satellites and these dwarf galaxies. So we don't actually predict very many in there. Okay, so that actually brings me to my conclusions. Right, so most simulators agree, right, that we can now make realistic dwarf galaxies. And a lot of the progress has come through, including a more realistic treatment of baryonic physics, right, that alleviated a bunch of problems with CDM galaxy formation theory. We've had a lot of success because galaxies in the classical range self-regulate, right? But now we're pushing down into this lower mass end where it's not clear that we're ready to interpret what we're going to find. I think that now we basically have to start worrying about these physical prescriptions that we're all taking for granted and start worrying about what is the most accurate thing so that we can make better predictions. Or we can turn this around, of course, and say, these are the things that are really going to put constraints on what prescriptions we're using. So I'll leave it at that.
Can you say a word or two about reionization modeling? Are we doing
Oh yeah, right. Yeah, so we haven't played around with that yet, right? So, yeah, obviously, right, like I said, it's reionization that's removing the gas from these galaxies before they can start forming stars. So reionization model is going to matter, right? At the moment, we just, we've actually got one that's too effective, right? It's the Hartmann-Maddow 2012, which is known for being too effective. But it's the same in both runs here. So we are, yes, one of the next things we're doing now is playing around with the different reionization models. And one of our collaborators is working on actually doing a ray tracing so we can do a more realistic reionization as well. But that's probably a year or more away at this point.
Can you say more about the H2 description and why at all do you care about the H2 and not like say?
Yeah, it's not clear that you should, right?
You don't need H2. I mean, maybe here H2 is where you form stars, but not necessarily needed.
I agree. Yeah. So yeah, I mean, I don't know how much I can say about this. There is a prescription at high redshift that you can form it in gas phase with no metallicity. Right? There's just a pressure term where you can form H2. And then it assumes your common thing where you've got some dust around so that you can build H2. And then we also track the Lyman radiation from the young stars in the UV background as a destruction mechanism.
So it's mainly from outside or from the inside?
But, well, we do follow it from the stars that are nearby as well. And so, yeah, like you said though, we then, in this model, require H2 to be present before you form stars. It's not clear that that is a necessary condition for star formation, right? It could be that H2, it seems to be a good tracer of star formation, but that doesn't necessarily mean it's the thing that's necessary.
But I agree that at low metallicities, it should be harder to form stars.
Sure.
So it's harder to form H2. It would be also harder to form stars.
Correct.
But not necessarily H2 is the right way to. Well,
Yeah. So Charlotte Christensen is one who implemented this model, and she's now playing around. She's actually got a paper in review on another mechanism where you simply look at the self-shielding of the gas. You no longer require H2 to be present, but is it shielded enough to go on and form stars, right? And so that may be a more realistic prescription.
I would say that if it's cold enough, like not just shielding,
Just so you think this would be accurate enough?
maybe something in the middle.
Okay, I'd like to hear more about that. Yeah. Okay.
There's a question about yeah, go on.
So in your first two conclusions that you're creating more realistic dwarves and you've resolved all of these issues with dwarves and the cosmological and simulations, how much of that is just a product of tuning the simulations to do that?
Yeah, we don't. They were tuned. I will. So sorry, I don't like doing these things, but also didn't want to show that. I don't know why that's popping up. Yeah, my daughter is now 3, but she, they like bottles, right? Okay, anyway, so we did tune to match this, right? So this is what we tuned to in the simulations to try to get out a stellar mass to halo mass relationship that looks like what abundance matching predicts. After that, everything else fell out of it. Nothing else was tuned. We didn't tune for size. We didn't tune for masses, gas masses, nothing else. No CGM, like Nihal claims, nothing else. Everything else came out of it, and then we just looked at these different problems, right, and found that we could find these resolutions.
So sorry, I came in late, so maybe you already touched on this, but one of the interesting things observationally is that at low masses, it now looks like there's a very wide range of sizes, right? There's dwarf irregulars, but then there's these ultra diffuse galaxies. And what I've noticed from other simulations is that either they can match one or the other, but not both, right? If they make feedback efficient enough to make ultra diffuse galaxies, and that's all they make at low masses.
Yes.
So what do you have to say about that?
So my 10-minute talk at the ITC luncheon is on ultra diffuse galaxies, so I didn't talk about it here. You want to wait? But they're not in these. They're not in these. I actually should say it's through a different set of simulations that does not have the resolution to make cores, and we still find ultra diffuse galaxies. So, be interested in chatting about it later.
Is there anything in your simulations that explains why we don't tend to see supermassive black holes?
So far they don't look very active, right? So we have, I guess that particular plot did not have. Okay, let me open up a different talk if you guys are willing to let me do this. Working? Okay, that's not on my screen, so I'm gonna actually open one that's on my screen. There we go. No, I guess I'm gonna have to work with this one. Okay. So this is the same stellar mass to halo mass relationship that I showed earlier. The galaxies that now have stars, those are the ones that end up forming black holes as well. So we have a prescription where rather than saying we're going to put a black hole in this galaxy when it gets above some mass, we have a prescription where if the gas particle meets certain criteria, right? So it's metal free, it's cold and dense, but not too cold, so that it doesn't fragment. It can go on and form a supermassive black hole. And so we get a bunch of gas particles turning into supermassive black holes at high redshift, like above redshift 6, and then we follow their evolution through time. So these are the ones that end up with black holes, and so far none of these actually end up even have any action in their history. They're never active black holes. But we have a second simulation, which is a 25 megaparsec volume, where we do have dwarfs with some active black holes in them.
There's
So
no gas. There's not enough gas.
there is not enough gas to feed them, I guess. Yeah.
You can have some tidal disruptions.
Sure. Yeah. Sure. So that's still an open area, but they're not very active.
Is this mass range the same range of masses as the dwarfs that come before us? Is it, there was like
Yeah.
a very narrow mass range?
Yeah, like in here. Yeah. Yeah.
To follow up on Charlie's question, so there is this paper by Sidney Chan that shows that in the ultra-faint dwarf galaxies, there's similar galaxies. The size of the disk or the effective radius is too compact compared to the observation. You said that you have realistic simulations.
Yeah.
Do you match that, or?
We do.
And what? I mean, because they tried all these kind of feedback mechanisms, they couldn't get it right.
It just came out of the, again, we tried to match a stellar mass to halo mass relationship, and then we ran these dwarf volumes and we looked at the size and things look okay. So let me see if I can get Dropbox open here. Somewhere in here I have sizes. How do I get it to show? Okay, I entered slideshow, but apparently that doesn't work. So these are the sizes that came out. So this is the half-light radii versus luminosity, and we've actually tracked down right down to about 100 parsecs here. We're matching local volume data, and that's actually down to like something like 40 star particles in a simulation, which is kind of amazing that still works. But
All right, cool. Let's thank